The final part of topic 8 involves just putting together some things that we already have learned in a famous experiment called Millikan oil drop experiment. And in this experiment in 1909, Robert Millikan determined the charge of an electron, and his team, grad students and stuff, were charging these oil droplets with a modified, if you look at the old perfume things that would squirt out perfume, they would go down a long, thin tube to get those into fine droplets. And out would come this mist of droplets from it. In this case, it was oil. But as these traveled, these droplets would travel through the long tube, they would become charged. And they would charge by chemistry. So they would pick up some extra electrons. Some of them wouldn't pick up any. And what they did with these was take them and put them between, in a uniform electrical field, between two charged plates. Hooked up to a battery of known voltage. And some of these particles would not have enough charge, okay, that the force of gravity would take over and they would fall down to the other plate. And some of them would have too much charge that they would rise up and go to the positive plate up there. But some of the droplets would have just enough to levitate, to float. Okay? And it's those drops that they became interested in. So in some sense, some droplets on their free body diagrams, some had Fg with an electrical force that was too big, and some had an electrical force that was too small compared to Fg. Some had the floating ones where the Fg equaled the Fe. And they looked at these and they knew the density of the oil and they could estimate the volume from the spheroidal shape of it, and from that they could determine the mass. So if we look here, we get Fe equals Fg, but Fe we know is Eq, and Fg is mg. So we can measure Q by mg divided by E. Okay. So we end up with this relationship here, like that. Now the field between the plates was voltage over the distance they're separated, and the mass of the drops can be calculated from the density and volume of the oil droplets. And they did this experiment over and over again. And the charge is quantized. So Q would equal some number n times the charge of the fundamental unit electron. So they would calculate this value of Q and realize that it's some whole number n times the charge of an electron. And they wanted to get at this charge of an electron. the least common factor of this would give us what the value of Q is. So to see that, and they came up first off with 1E was 1.6 times 10 to the minus 19 coulombs. And the least common factor, the way they would do that, so just for an example, say they got the value of a 6, okay? And this is we're simplifying it here. Well, 6 can be divided by 6, it can be divided by 3, and divided by 2. We'll ignore the 1. Everything can be divided by 1. 24, let's say we got for another value of Q. And that can be divided by 24, 12, okay, 8, 6, 4, 3, 2. We do it again and we see we get the number 18. You know, that can be divided by 18, 9, 3, oh, and 2. And then let's say we do it again and we get value of 9. Well, that could be divided by 9 and then 3. So taking a look at that, we can see here what's common in all of them. Well, this has a 6, and this one has a 6, and that has a 6, but that's it. Oh, this would have a 6 too, but not this one. And the one that matches up in all of them is 3. So that would be our fundamental value of an electron. Of course, in our case, it's 1.6 times 10 to the minus 19, actually. And from that, we're able to determine the charge on an electron was. And we'll do a version of this experiment with values of mass in lab.